And now we get to my favorite lab in the whole wide world, the Binary Bomb Lab. So this comes from the Carnegie Mellon Computer Architecture class by Professors Bryant and O'Halloran, and I appreciate them providing the source code for this lab so that we could port it between different architectures. Originally, it's provided in the context of x86, and the students only get a x86 binary, but they provided us the source, so we compiled it for RISC-V. They also wanted me to mention that the class textbook is available here, and you can thank that textbook for me drawing the stack diagrams the way I do. So what is the goal of the Binary Bomb Lab? You are given an opaque binary blob, and you run it, and you have to figure out what input does it want to not explode. So fundamentally, this is a reverse engineering exercise. And when I first had this class, not at Carnegie Mellon, but at the University of Minnesota, this ultimately got me interested in assembly and reverse engineering, and it's been really foundational for my learning ever since. So what I'm going to do is I'm going to walk you through the first phase of the bomb, and then I expect you to do all 5 remaining phases on your own. When I was first doing this as part of the University of Minnesota class, I did it with a partner, and between the two of us working on and off, it took us something like 2 weeks. Now, when I was first taking this class at U of M, I was also trying to put myself through school and pay for it myself by working night shift at a hotel, meaning I worked overnight. And they told us that that would allow us to do our homework and things like that, but that really didn't ever work out. So my first semester, or my second semester at my freshman year, basically I got 3 C's and a B, and I got a C in the computer architecture class. So although it took me 2 weeks to finish this with a partner the first time, I went off and didn't want to have that C on my record, so I retook the class later on in my college career, and the second time through, it was much, much easier, and that's the way it always goes. The second time through is so much easier. If you take this class again in a year, I guarantee it will be ridiculously easy. So the second time through, instead of 2 weeks, it took me about 2 hours all by myself. So this is a lab that can take quite a lot of time, or it could take not much time at all. If you've seen it in other classes where we use it, it may go relatively fast, but don't worry, we have an expert mode for you. Okay, I haven't decided where exactly we're going to place this binary bomb in your labs yet, but I've placed it in my home directory. So if I just execute the bomb like that, I see it say, "Welcome to my fiendish little bomb. You have 6 phases with which to blow yourself up. Have a nice day." And then it's got a blinking cursor. If I hit enter a few times, a whole bunch of nothing happens. If I type some characters and hit enter, oh, boom! Then I got a boom. The bomb has blown up. That's not what I want to see. So, of course, I could brute force this and type a single A and then type 2 A's. But that's not the smart way to go about it, right? We know how to use a debugger, and so we need to figure out, where does it print out boom? How do I avoid that? What sort of input would cause it to not go boom? So I'm going to cat out my x.config just to show that right now I'm going to be printing out the return address, the program counter, the frame pointer S0, the stack pointer, and arguments 0 through 5. That's just what happens to have been in my x.config at this point after fiddling around in all the other labs and stuff. I'm gonna print out 14 giant words, 14 64-bit values from the stack pointer, and print out 20 instructions before setting a break on main and running the program. So let's go ahead and start up the bomb in the debugger, gdb-x and /x.config and the bomb. When this starts up, it'll give me all of my registers that I want to see, and it'll also give me 20 instructions of main. Okay, so GDB is showing me my registers that I want, my stack that I want, and also 20 assembly instructions. If I want to see the full main, I can do disas for disassemble and main, and that'll give me the full thing, and I can continue on. And so if we just skim, again, this is the big secret of reverse engineering, look at it at a high level, then go down to a low level, then look at it at a high level, then go down to a low level. So at the high level, our initial skim tells us we've got calls to fopen, so there's going to be some sort of file opening. There's some sort of call to initialize bomb. There's putS, which we know is printing stuff out. PutS, a function called readline, a function called phase1, function called phase1 diffused, put s, so print something out, read line, phase 2, phase diffused. So printing, reading, phase diffused, printing, reading, phase diffused. So there's a general pattern going on here, and that looks like that continues all the way down to phase 6. But we're focused on phase 1 right now, and we want to figure out how do we get from phase 1 to phase 2, first of all, or more to the point, does it explode in phase 1? Like if I step over phase 1, do I see a boom, or is it somewhere else that's occurring? So our first, question and hypothesis to ourselves is we will hypothesize that if we step over phase 1, that it'll go boom if we give the incorrect input. We will test that hypothesis by copying this address, setting a breakpoint, and continuing on. Okay, we continued, and we're now at this input where it seems to say, or this output where it wants some input. So I'm going to type hello, and I'm going to hit enter. So just typing hello and hitting enter, it has not yet went boom. We are still in the debugger. It is still continuing on. So we are now at phase 1, so we can eliminate any idea that the boom happens before phase 1. It cannot happen earlier than phase 1. Next, we want to see, does it happen inside of phase 1? And to test that, we're going to go ahead and step over it. We're going to use the NI for next instruction. That does not go into, that's basically like a step over. That's not a step into. So we will step over this instruction, hoping that we reach the next assembly instruction. So hit NI, but no, that did not work. Boom, the bomb has blown up. So somewhere in phase 1 is the boom, and we need to find where that is and avoid it. So the next thing we could do before we restart the process is we could go ahead and disas phase 1 and go ahead and look at, we can go ahead and look at just phase 1. So this is the phase 1. So we could look at every single assembly instruction, figure out what they all do right now, but let's not do that. Let's start with a skim. And the starting with a skim is that we see something called strings not equal. We see some bnez. We see an explode bomb. So that's kind of interesting. A strings not equal call and an explode bomb call in here. Kind of makes me think that this conditional control flow, the branch if not equal to 0, that's checking the argument 0, which is going to be the return from strings not equal. If bnez, it's going to branch if this is not equal to 0. Where does it branch to? Phase 1 plus 24, and that is phase 1 plus 24 branch to the explode bomb. So if that's not equal to 0, go to explode bomb. Otherwise, if it's 0, then it's not going to go to explode bomb, and it's going to continue on and return. So that's what I mean about, we don't want to just start by reading every single assembly instruction. Let's only read them if they seem relevant to our goals, and our goals are to avoid the explode bomb. And we can see that we get to the explode bomb by the result of a jump, a branch that has to do with whether or not this output of the strings not equal, walking backwards. If the output is not equal to 0, we go boom. So all right, we've got ourselves some clues. We've got enough to go on right now that let's go ahead and restart the program. R for run, we're running the program with no command line arguments. And we continue on, and we have previously set a breakpoint on that phase 1, so let's just go ahead and continue. All right, here's my request for input. I'm going to say hello question mark, and I'm going to go ahead and step into this phase 1, SI for step in instruction. We are now inside phase 1, but I really want to get to this strings not equal. So I want to see what are the inputs to a function called strings not equal. And just walking backwards from that, I can see, well, there's an A1 being set, and so there's no other A0 explicitly set here. So maybe it's just using whatever's in A0 at the time we come in. We don't know, but let's go ahead and assume that A1 is an argument being passed to this and that it has 2 arguments for doing some sort of strings not equal comparison. So let's go ahead and step our way right up to that call, the JAL. We want to see right before we call into this thing, like we clearly haven't gone to explode bomb yet, our hypothesis is that these argument, the A0 and the A1, are arguments to the strings not equal. And we don't know what kind of arguments they are, so we could examine them as various things. We could say, let's look at it as if it's 10 bytes, or let's call it hex bytes. And let's put that address. and that'll give us 10 hex bytes at that value. First of all, we should also say that they really look like pointers roughly into the code area. So we can see they don't start with like 7 FFF and something, so they don't seem like they're pointing to the stack or anything like that. They seem to have the same general address range of all 5s that we see with the code itself. So we don't know what those arguments are, but we do know they're probably not pointing at the stack. So if we look at the memory at those addresses, we see some values, and maybe those values look suspiciously within a small range to you. Let's look at the other one. Let's look at this thing, 10 hex bytes at that address. All right, some more values that also are suspiciously in a small range, in the 6-ish range. Well, let's go ahead and just call a spade and say that let's examine it as if it is a string. Maybe it's a string because those look like ASCII character ranges. And indeed, if we examine as a string, this second argument seems to, so that was the argument 1. The second argument is a string, the moon unit will be divided into 2 divisions. And if we did the same thing and we pointed it at argument 0, we have hello. And so that is our input. And this is some other input, some other string, some other pointer to a string that is being passed into strings not equal. So 2 apparent pointers to strings passed into strings not equal. Well, I would hazard a guess that the result of strings not equal is going to be based on whether or not these things are the exact same string. So let's go ahead and NI, next instruction, step over this. Strings not equal, we got here, we're bines. The A0 value is 1. So is 1 not equal to 0? Yes, that is true. So we're going to branch, step I, and we're going to branch to the explode bomb. We don't want that, right? We want to avoid the explode bomb. So we must necessarily make sure that whatever comes back from the strings not equal is going to be equal to 0. Not equal to 0. It needs to be exactly equal to 0. So now at this point, if we were, a novice reverse engineer, we would say, disassemble that function and let's go read that full thing and figure out how it works. But I'm not a novice reverse engineer, so I try to do things the easy way. And the easy way here says, I'm just going to do a quick test and I'm going to see what happens if I give the same sort of input that was being passed into this. I'm going to give this particular string that I saw used here, that was not my string, it's just some other string. I'm going to give that as the input. Then I'm just going to let this entire code run and see what happens. Like, this is the difference between pure static analysis. If we had pure static analysis, we would have to read everything and try to figure out what's going on. But we're doing dynamic analysis here. We have a debugger. We can go ahead and just test things as they really are. So let's go ahead and rerun the program. And let's give this new magic string as the input. Continuing on, pass our magic string we saw used elsewhere, and step into the phase 1, step, right up to the point of strings not equal. We're going to look at our arguments. We see the first one, examine as a string. That is the moon unit. And the second one, examine it as a string. That is also the moon unit will be divided in 2 divisions. So let's just test our theory. Next instruction over it. And what is A0? A0 is 0. So if we step, we no longer go to the explode bomb. If we continue, we see phase 1 diffused. How about the next one? All right, so that is where I'm going to leave you with my initial walkthrough. It's up to you from here to figure out what inputs are needed for this binary to pass phase 2, pass phase 3, and so forth. Okay, well, that was the first phase of the bomb lab, but now you've got to do all the rest of the phases of the bomb lab. So if you've seen this before, or if you've already learned some other assembly language before this, which I expect many of you have, probably RISC-V is not your first ever assembly, I recommend you do this in expert mode. And expert mode means take away those helpful symbols, the things that tell you where phase 1 is and tell you where initialize bomb is. Take away the symbols by running the strip command. So run strip on the bomb, and then now you won't have any nice helpful symbols. It'll be a little bit harder. Although if you've got reverse engineering experience, it won't be that much harder. But it'll certainly take you more time than if you had symbols. And the final hints for this lab is that you need to remember to read the fun man pages. You will be encountering C functions that perhaps you don't use every day, and you need to go off and read the man page for those functions so you understand what are the arguments in, what are the arguments out. The other thing is that this is just general reverse engineering guidance, especially for those who have not reverse engineered a lot before. When you're reverse engineering, it can be very tempting to try to understand every single assembly instruction and go one by one and drill into every single function. It is generally my guidance when doing reverse engineering to dive down and then come back up, and dive down and then come back up. You basically don't want to get too caught up in the weeds. You have to think to yourself, what is my core goal here? And your core goal in the binary bomb lab is just make it not explode. So you need to always be focused on, is what I'm figuring out right now about the binary, is it going to help me not hit the explode bomb function, and to avoid that and to continue on and be able to transition into the next phase. So it is reverse engineering to go backwards and say, hey, I need to get here in the code where it's not going to hit the bomb. Walk backwards, and what inputs do you need for that to be correct? What conditions need to hold true, and how do you achieve those? Okay, well that's it. Now I want you to run off and do the binary bomb. It's going to be fun, trust me.